like. Does anybody have any thoughts or general questions or conceptual ideas about this whole notion of a heuristic and of a heuristically informed search? Yeah, Dan.
I've got a question just before one that was mentioned because I wondered about it. If you do the left wall or the right wall search, is that the same as a depth first search?
It can be.
It can, but it's not always.
Right. So essentially what you would wind up doing is emulating a depth first search by giving low numbers to things that are getting close to the conclusion. And you really actually do wind up doing something like depth first search, yeah. Yeah, and so that's going to be, again, something kind of wildly unpredictable. I think the reason that this left-hand rule is popular as advice for getting out of a maze is that it gives the explorer a consistent and easily understood strategy. That is, if you always go left, you'll exhaustively eventually get out because you have a consistent strategy where it's not difficult to remember what you're supposed to do next. And that in turn keeps you from like revisiting the same old stuff over and over again. So that's part of how you can think about it. Good. Other questions, thoughts, or anything coming off of the discussion we just had? All right. So part of what I'm going to do today is I'm actually going to spend some time walking through a lot of the code I gave you and explaining precisely how a lot of it works. This is the kind of assignment where the coding I'm having you do is aspects that I consider maybe the conceptually most essential. That is, thinking about the Maze Explorer is a matter of thinking about the whole process of what does it even mean to generate a successor? Ultimately, if you were to do something like A* for some other problem or some arbitrary problem, for every new problem you have to think about where do successors come from? And so I wanted to give you some exercise with that process. Similarly, when it comes to the heuristic evaluation, I wanted you to think about starting with breadth first search. At a low level, what are the changes I need to make it best first? What are the commonalities? What are the differences? So with all of that said, I'm going to jump on over to the code. And what I'm going to do is I'm going to begin with this bestfirstsearcher.java, talk about the different aspects of the implementation, and make some comments about how it's going to interact with what you'll need to be doing as part of your own coding process. Some of you have already gotten this working, which is great. But even so, there might be aspects of it that I hope I can illuminate in this discussion. So I guess a quick question. Back row, is the font sufficiently large for you to read? One up, David? All right. All right, now I got to remember how to do it. Oh, no apologies needed. Actually, anybody know? Control plus? Maybe Control Alt plus. Maybe Control Alt Shift plus. Maybe. Yeah. Definite points for serious cleverness. Okay. View. Where's preferences? Oh, I go to settings. It does in its own way. If I go to settings, appearance, editor, font, and I guess we can just kick the size up to 18. What do you think, David? All right, cool. Okay. So, thank you all. So, this class is Best First Searcher. And the generic type is that it says it can take any generic type T as long as it extends best first object. So as is often the case with a constrained generic, we need to actually look at that type to know just what it is that we're getting. So if we go to best first object, these are the critical methods. There's a method called get successors that gives you an array list of the things you're looking for. So notice that the Maze Explorer implements this, right? Then it gets a hash code, which winds up being important because I use hash sets all over the place to store this stuff. And then it's got an equals method because hashing. And then there's this achieves method. So the point of the achieves method is to say whether a given a goal, has the object achieved the goal. So by using this constrained generic over here, what we're saying is whatever our T is guaranteed to have these methods. That's what we're doing. All right, so we go in, what do we have for data? We have an array list T, which is the solution. That is, a solution is going to be a whole sequence of objects that gets you to where you want to go. So specifically, if we go down to solve, at the very end, there's this reconstruct moves method. And what reconstruct moves does is it actually systematically adds elements to this solution. So part of what we're doing here is this best first searcher isn't just a search algorithm. It's also a data structure that maintains a record of what happened during the search so that you can constructively use the outcome. See, in principle, right, we could just sort of have an algorithm and have it say, okay, found it, life is good. But we actually want to retrieve it, which is important. Depth and num nodes, that's statistical information just to tell you how did it do. So including that is not essential to the algorithm being correct in any way. It's included so that we've got a way of getting experimental data about what we're doing. Here we've got a reference to a best first heuristic. So this object is simply keeping track of how far does a given node need to go to get to the exit. So best first heuristic is also an interface, but this is a very simple interface with one method. Get the distance from the node to the goal. I want to emphasize here that what we're really trying to do with a design like this is to keep independent parts of the algorithm decoupled from each other so that you can think of them as interchangeable pieces. That is, this one implementation is perfectly happy to function with any data type that can generate successors and tell you if it got to its goal. It's also happy to use any heuristic that takes an object of that data type and makes an estimate. And all of those things can vary independently, which is really handy for experimenting with different configurations. And then we have this Boolean variable solution found. Not so much with the maze as we've constructed it here, but thinking about search in general, it's possible for a search to fail. Now, in this particular case, it is carefully designed to never fail. What do I mean by that? What I mean is every maze that my maze generator generates actually has a path from the exit to the goal. It's not difficult to imagine, however, a maze generator that doesn't make that guarantee and just lets the poor explorer wander around and be trapped, right? That's conceptually possible. And so it's important that our search algorithm have a way to say, I have tried every possibility and there is literally no way out. Having this variable here to signal that is very useful then in case something like that were to emerge. So solve is the keystone method of this data structure, okay? And so when we talk about solve, we're saying we've got some object that's at a certain start state. So that could be at the entrance or it could be somewhere in the middle of the maze, right? And then we've got a target. This is the thing we want to be at. So the first thing we set up here is a visited set. Well, the visited set is really, really important because when we're doing best first search, you might remember from working on Maze Explorer, you generate just like all the neighbors. And you always do that every time. That's part of the process of decoupling the logic into different sections to make this reasonably straightforward to create. By just saying get successors just kind of spams everything, you take away the need to keep track of have I been there before. In turn, the solver accepts the responsibility to keep you from going around endlessly in loops. And this visited set is absolutely crucial for doing this. Then search node best is not the best search node ever, but rather represents an idea of the best thing I know about so far. And at the beginning, it's a search node with no parent located at the start value with a given target value. Now, what's the point of the parent business here? When we get to the search node, I'm going to walk you through that. But essentially, the idea is these paths through the search space are singly linked lists. And the links in the linked list point backward to the node that brought it into being. That is the mechanism by which we're able to retrace where we came to constructively create a path at the end of the search. If we don't retain that information, then the search says, yeah, a path exists. Good luck finding it. Which, while admittedly funny, is not fun. Next, we've got our queue. And I went ahead and just used the standard doubly linked list to represent my queue. So remember, the queue lets us put things in with add and remove things with pull. So add adds something onto the end of the queue, and pull removes from the start of the queue. So I initialize the search by giving it one node that represents being at the very start of the maze, or whatever problem I'm solving. So then down from here, I'm going to set my solution found instance variable to false. Why? Because I haven't even started yet. If it's true, I've got other things I need to be doing. So now my while loop has two conditions, right? Or a compound condition. First, I need to make sure that my open list, the list of things I'm willing to consider, has more than 0 elements. If it has 0 elements, too bad. There's nothing left to search at that point. And that's why the solution found distinction is so important. If solution found is false, and there's nothing in the open list, the search has failed, and there is no solution to be found. And then we also say, we're only going to continue as long as the solution hasn't been found. All right, so we go in, we grab something from the queue. We know this will work because we've guaranteed that there are more than 0 elements. So there's a close tie between the operations inside the loop and the way we structure the condition. Then, as it happens, the very first time I wrote this, it was not bug-free, and my debugging code is still in there. So now we check to see if our visited set contains the object that we just removed. And if it contains it, we just skip this and we go around. In other words, if we grab something from the queue and we've already tried it out, we're just going to toss it aside and move to the next item in the queue. It's really important that we defer this decision to this point, because especially once we're doing best first search, we don't know ahead of time how things are going to land in the heap. Like, we don't know if this is at what point it's going to end up or what have you. So it's important that we kind of defer until this point, as opposed to at this point we were adding the successors. So anyway, let's say we haven't visited it before. The first thing we do is we mark it as visited. Don't want to see it again. Now we ask, does this thing achieve the target? In other words, have we reached the goal, however it's defined abstractly for this problem? If it is, we set solution found to be true. By doing that, this loop will then cleanly exit. Otherwise, we add successors. So when we add successors, we ask our object for its list of successors. And so this is then calling the code that you write for Maze Explorer. Okay? And for each of these, we add 1 to num nodes. So it's valuable to grasp that when we talk about the total number of nodes expanded, what we're talking about is how much stuff have we put in the queue like ever. And so that accounting happens here, so you understand where that number is coming from. We then create a search node object. And I'll be going over that class in a moment. But the general idea of it is it's all the information that the user provided along with this notion of the parent links, so you can trace things back. Then our depth is going to be the maximum of the current depth and the depth we get from the new node. In other words, as we generate successors, a lot of them are going to be at the same depth. So we don't want to just add 1 to the depth every time. What we're trying to do is make sure our depth is the max of everything we've ever seen. Since everything we've ever seen must go through here, then we get it. And then finally, we add it to that open list, which is passed in here as a parameter. So having done all of that, that is a generic search algorithm. Note that I could take that queue out and put a stack in, and I suddenly have depth-first search. So the way that this data structure arbitrates the order in which we visit the various nodes is what gives different search algorithms their distinctive behaviors. And we're exploiting that in converting this breadth-first search to best-first search by swapping in a priority queue there. Any questions so far? Yes?
So if this already checks if we visited an area, then Maze Viewer, or Maze Explorer, do we not need to check if the successor has already been visited?
That's correct. So, and this is part of the idea of kind of separation of concerns. So the Maze Explorer's only job is to say, from where I am, this is where I can go. That's all it needs to do. And the reason we do it this way is no matter what your data representation is, making sure that you don't go back and repeat a visit is something that any searcher will have to do. So because that's the case, that belongs in this part of the code. Yeah, Mitchell.
I was just kind of confused on what the point of the depth variable.
The point of the depth variable is just to understand how far the search went before it gave up. Like how deep did it have to go from the starting point to get to a particular value? So part of what can happen is that in something like a breadth first or a best first search, the depth and the length of your final solution should be the same value because they guarantee a minimum length solution. In something like a depth first search, what could happen is your maximum depth could actually exceed what you find. So imagine, for instance, you've got a maze with a path that has some long pathway that ends in some kind of a dead end. And the length of that pathway that ends in the dead end is longer than the path that actually got you to the exit. So something like a depth first search would then report a depth that actually exceeds the length of the solution. And so that's useful to know because it tells you something about the underlying dynamic of the search. In the case of best first search, if that happens, you know you've got a non-monotonic heuristic. And so that's like a bit of experimental evidence that can either confirm or refute whatever logical reasoning we did to come to a conclusion about its monotonicity. So, great question. Other questions so far? Any other questions? Yeah, Innocent.
How is the heuristic very useful in this particular algorithm?
This particular algorithm does not use the heuristic. This is just breadth first search. To get to best first search, we put in a priority queue. And now, in order to know how things are ordered in the priority queue, we need the heuristic. So that's the second part of the coding part of the assignment. Yeah. But as it stands, this just doesn't use it. I'm going to point out where you're going to plug in to use it, though. Other questions so far? Yeah, Dan.
When you're doing a best first search,
Mm-hmm.
when does it go through and recalculate the values of the nodes? Like if you start out at the top and you had 2 nodes and you assign a value of each of them, and then you go down one way, does it ever go back and reassign that value up at the top?
No, as soon as the node is generated, its value is set in stone. And that's a really important point. I'm glad you brought up the question. Once a node's generated, the estimate just is what it is. There's nothing that can happen that can change that estimate. Of course, successors to that node in some manner should have more precise estimates. Because the further you go in the maze, the more information you have that should lead to a more precise way of thinking about it. But for each individual node, once you've calculated it, bam, that's it. And it's actually important to calculate it only once, because there are times where the heuristic evaluation is a sufficiently expensive operation that you just don't want to do it more than once. Expense is relative, right? We're doing a graph search. That's really expensive. Worst case, what we're doing is essentially exponential time. So what best first search does is it kind of gives us a way to put off the exponentiality a bit. But still, if you've got, say, a quadratic algorithm for calculating your heuristic, well, you want to run that as little as possible because you're calling this algorithm on every single iteration of the search loop. Does that make more sense of it? Other questions so far? Those are terrific questions, by the way. All right, so if the solution is found, it reconstructs the moves. To really understand all of this, though, now requires looking at the search node class, which is part of what you need to modify as part of this assignment. So this search node class is implemented as what is called in Java an inner class. So this isn't necessarily something that's used an awful lot. Inner classes are handy because objects of the inner class have access to all of the data members of the class that it's part of. In this case, that utility comes into play when I want to contact my heuristic. Because search node is an inner class, it can just talk to this h variable right here. So that's largely why I did it this way. So you've got this search node class. What's in it? It has a depth, it has a t, so whatever the data type is of the thing you're exploring. In this assignment, of course, you'll have a maze explorer plugged in. And then it's got a parent. So each search node has a search node that's a parent. That's what makes these search nodes effectively into singly linked lists pointing back to the start. Let me sketch out for you conceptually what this winds up looking like. So at the very beginning of the search, I've got that first node that I put into my queue. Let's say it has 2 successors. Each of those successors has a parent pointer going back to that node. Let's imagine this one itself has some successors. They point back, they point back. And now let's imagine here's a successor that actually defeated the maze. It won. It's the way out. So now to find out what moves I had to make to get here, I can follow this trail of nodes back to the start. So what I have then is effectively a singly linked list going back to the start. Granted, it's only a singly linked list from the point of view of a node that's effectively at the start of the list. It's really like a family of linked lists that are all sharing the last parts of the list. This is an example of linked lists kind of at their best. Especially those of you that have taken data structures from me specifically might be aware that I'm not always terribly kind to linked lists as a data structure. I think that there just aren't that many circumstances that really warrant using them in comparison with arrays. But I think this is a really nice example where linked lists really come in on their own as having a lot of utility. Especially when you imagine a really large search tree, which is what this is a search tree. The fact that they're sharing a lot of suffixes is very memory efficient, and really is the linked list at its best. So that's what we have here, is this implicit linked list that comes from these parent nodes. So in the constructor, what it does is it gets a parent node so that it knows which way to go. Now, going back up here, we see that when we create the very first node, its parent is null. Why? Because it's the first one, and you got to stop somewhere. If you don't, it's a circular linked list, which, while entertaining, would not be helpful to us as we reconstructed a solution. Okay. That's that. And then we've got our node. And now IntelliJ has grayed out the goal over here. Why is that? Because mysteriously, I have no references to it. It's as if I took my completed solution and deleted some code at this point. As if. So what am I getting at here? What I'm getting at is, and this relates back to Dan's question earlier, this is the point at which you want to invoke your heuristic. That is, you've got a node, you've got a goal. Let's review what the heuristic wants. It turns out it wants a node and a goal by some fascinating coincidence. So coming back here, you've got some node, some goal. You can then ask H, the heuristic, what's the estimated distance? Then what you do is you add an instance variable, some int, in your search node to save that number. And you take care of that right here. So we can ask for the depth, we can ask for the underlying object, and we can ask for the parent. Yeah, Eric, do you have a question?
Is it necessarily advantageous to have to store that as an int as opposed to like a double or something like that? Because theoretically, you could have a heuristic which is kind of compresses a little bit more, right?
So in general, an int is preferable because of the rounding errors associated with doubles. So it tends to be a precision issue, basically. So with an int, as long as your estimate is 2 billion steps or less, now I'm thinking I really wanted a long here, but that's okay. As long as you're about 2 billion or less, which with our mazes shouldn't be a problem, right? You have guaranteed precision to the ones place. I tend to be really reluctant to use doubles unless I really find it compelling. And that's because the arithmetic aspects of a double often lead to rounding errors that often have unintended consequences.
Right, but is it possible that you have a heuristic that says, well, both of these are about to, but one of them is very slightly preferable to another one?
Oh, I see what you're getting at.
Whereas just rounding that down to an int could kind of.
So you're getting at the notion of precision or whatever with that. So here we come back around to what the real intent of the heuristic is. So the real intent of the heuristic is to count in integer terms, how many more steps do I have to go? So a fraction is not meaningful semantically in that context because there's no notion of a half action in this kind of a search. There are other kinds of searches where that is a meaningful notion. Typically what happens there is that this is effectively an unweighted graph representation. You could imagine a weighted graph representation in which the weights are doubles, and now you've got sort of more fine-grained ways of thinking about it. But when the heuristic estimate itself is really just asking, how much farther do I have to go? The notion of a double is not really helpful as a model for what we're looking at. But I see the intuition that you're getting at there. So great question. Other questions so far? So in order to throw these into a heap, they have to implement the comparable interface. And so on a programming level, you'll be saying implements comparable search node. And then in IntelliJ, you can say Alt-Enter, implement methods, and then it will give you compare to. So compare to is this Java-ism that performs an arbitrary comparison between two values. It returns a negative number if the first value is less than the second value. It returns 0 if they're equivalent, and it returns a positive number if they're greater. Subtracting the heuristic values actually works really well to implement this. I'm going to undo this back. There we go. Unpolluting my code. All right. So that's the search node. Any questions about this? Okay. So to reconstruct our moves then, what we do is we give it some search node, which is the node that won the war, that got to the exit. We say, well, that's not null. We're going to add its object to our solution array, and then we're just going to ask the searcher to look at its parent. So this while loop is a basic traverse a linked list all the way to the end, and then stash everything you find in this solution array. Of course, the trouble with this is that it's backwards. So this for loop reverses the array in place and makes it forwards. So that's really all that's doing. So that's the search code. It's one thing to draw pictures and think about this in the abstract. It's quite something else to think about it as code. I hope this helps make more sense of fundamentally what a search algorithm does and how the best first variant fits into the picture. Any questions about this? Yeah, David.
I just had a question about how your interfaces, when you just add one to heuristics, how does that actually get implemented into the how does that get used when you click it? And because when you add one, it says it never uses it. And I was wondering how the interface.
Oh yeah. So what David is asking about is every time you create a heuristic, I told you to put it in this heuristics directory here. And then when you run the program, there's this drop-down menu that lets you pick a heuristic. Right. So just to illustrate that, right, if I go to Maze Viewer and run it, I have my drop-down menu here, and right now it's only got breadth first. So now let's say I come down here and I copy it. I'm going to call it breadth first 2, just for illustrative purposes. And now I'm going to run Maze Viewer again. And now I can pick between them. Of course, they do the same thing, so they're not interesting. But I can pick between them. So David, your question is, how does it do that?
Yeah, just how does get distance?
Okay, so this is sort of a multi-part answer. The GUI is set up so that when you pick a value from that box, it uses in a slightly wonky part of the Java standard library known as the reflection API. So what that does is it lets you do something like, here's a string. Now, build an object of a class with the name that corresponds to this string. So that's basically what it does, is it first goes through this heuristics directory and populates that drop-down menu with the name of every class it finds in there. Then, when you tell it that you want to create a heuristic, let's see, this is the class where all that stuff happens. Yeah. You give it the name, and then I think I wound up setting up a hash map that takes the name, and there's a class that lets you create objects to the class and so forth. So it's kind of, yeah, here we go. So the heart of it is there's this forName method where you give it a string, which is the name of a class, and it gives you a class object, which then lets you create new instances and so forth. So that's how all that works. Well, kind of is until you do it. Yeah. But that's the basic idea. Cool. Mitchell.
So for the heuristics,
Yeah.
so for the breadth first search, you got it where the maze explorer is what's put in there, but we put in nodes, like the interface wants nodes, but the breadth first search has maze explorers. So like for the new heuristics, what should we use?
Oh, that's a great question. So notice that this sort of dummy heuristic here, breadth first, implements best first heuristic of Maze Explorer. So that means that both of the parameters it receives are Maze Explorer objects, and it can ask stuff about them. So let's imagine actually coding something like this, right? So let's say that our heuristic is the, I'm trying to think of something kind of useless but illustrative. Yeah, there we go, right? That'll actually do it, yeah. So if I take node.getLocation, and I'm not giving away a whole lot here by saying there's this get Manhattan distance, right, to goal.getLocation, right? Right, so there you are. That's the first heuristic for everybody. Yeah. So what I'm doing is as I implement this heuristic, I'm using these two objects to get the information I need. Something really important I want to emphasize here that I've said to several of you in office hours, but I want to make sure everybody's aware of, is if Maze Explorer as it stands isn't advertising all the data that you want to use for a heuristic, by all means, add methods to it. Like, totally go to town. If there's data you want about the Maze Explorer that you want to use in a heuristic, just add methods. In general, right? I mean, there was one student I was talking to, I forget who at this point, who was kind of like, well, I was reluctant to add any methods or instance variables because it seemed like it was cheating or something or whatever. No. I've given you kind of an infrastructure. I want you to work within certain bounds just so that it doesn't like crash with horrible bugs. But if you kind of entrepreneurially want to advertise information in particular ways, have at it. Have a great time with that. Especially when it comes to something like Maze Explorer and building heuristics that make use of it. A lot of you had a lot of creative ideas. I want to make sure that your heuristics have all the data needed to actually undertake those creative ideas. Yeah, Innocent.
How can I get treasures from this method right here? Like, if I want to do stuff with treasures.
Yep, and that would be one reason why I suggested you might add some methods. Right, so if we come on over to Maze Explorer has a reference to a maze object that it's exploring. Now, as it stands, it's not really advertising any information about the location of the treasures. And what I'm suggesting is feel free to advertise that as much as you want. For example, I could create the following method. Public set maze cell, get all treasure from maze. And that'll return m dot get treasures. Oh, and now it doesn't know what a set is. But now it does because of Alt Enter. So now I've added that, and now in my heuristics, I can get that as much as I want. I might even want something like this. Public int get num treasures found. And I could then return treasure found dot size. And bam, now I've got that available for my heuristics. So I deliberately didn't include any of these in here because I wanted you all to kind of think about, well, what do I need? And then give you all kind of the freedom to build whatever methods you need to get the data you need to do your heuristics. So whatever that looks like for you is what I want you to go ahead and code up. Does that make more sense of it, Innocent?
Yes.
Cool. Other questions so far?
Does it need to just be about this?
Other things, sure.
Okay, can you talk a little bit more about like the experiment part of this?
Yeah, sure. So, bam. Oops. Sorry, wrong class. Okay. So for the experiments, so for each heuristic, determine experimentally the hardest mazes it can solve in 2 minutes or less. So really what I want you to do is kind of mess around with generating mazes, varying these factors. How big is the maze? How much treasure does it have? The perfection concept and so forth. And see how big can you go until your heuristic is beaten. You know, can you go to 100 by 100, 1,000 by 1,000, 10,000 by 10,000? At some point, you'll hit a point where it's like after 2 minutes, you just give up. So one way to think about this is initially, as you're developing your heuristics, you'll mess around with vaguely smaller mazes and get a fairly good sense about their relative competency. From there, you can start going to larger mazes and begin by, for the largest, as you go to each larger maze, start off with your best heuristic, right? The one that's going to do the least amount of search. If that one gets killed by the maze, then you know they're all dead. And so at that point, you would go to something smaller. What's key, though, is when you generate a maze, you got to run all your heuristics on that same maze so that the comparisons are apples to apples. Yeah.
So we don't record data of any smaller mazes. We only record data from the maze that is the largest that all of our heuristics will work on.
Yeah. Yeah. You know, so that'll be fine with me. Yeah. But that said, you might have different ways of thinking about the hardness, right? So you might have a really big maze with like 2 treasures. You might have a smaller maze with 10 treasures. And so as you experiment, one, you include both of those. But you don't have to include sort of like the ones where you're ramping up. Because at that point, like there's just not a whole lot some of that data even tells us. You know, it's more interesting to think about for each extreme, what got me to that extreme and what did I learn from that extreme? That tells us a lot more. Cool. Any other questions on this? Yeah, Mitchell.
So when the best first searcher is called for the first time, is the generic that passed through that, is that the Maze Explorer?
Yeah, it'll be a Maze Explorer. Yeah. Yeah. And it's not so much when it's called for the first time, it's actually set at compile time. Yeah, that's the way the generic types work in Java. They're actually checked at compile time. Innocent, you had a question.
There's another drill like when a maze got beaten. Like, what do you mean by beating? But a maze
Oh, by exiting it with all the treasure.
Oh, like finding a path to the
Yeah.
end?
Yeah.
Okay. Yeah. That means being beaten is like not finding a path.
Oh,
Okay.
I see where you're confused. I was using the language somewhat imprecisely. Because we could have the notion that the explorer beats the maze, or we could have the notion that the maze beats the explorer, and those mean completely different things, right? So if the explorer defeats the maze, wins the maze, that means that a path exists. If the maze beats the explorer, it means a path does not exist. So yeah, it was a little sloppy there. Sorry about that. Cool. Other questions? Yes.
As for recording the experiments, do you just want like a screenshot of the ones that broke it, or?
I just want a table
Okay.
with numbers. Yeah, I mean, screenshots are fun. Feel free to use it, but I'm perfectly happy with tables with numbers. And yeah, I am definitely trusting you all to honestly report what you saw, and I don't feel any particular value in auditing it by looking at your mazes, if that's what you're wondering. Cool. Other questions? Other questions? All right. Well, it is close enough to 4 that I think we're going to call it a day. I look forward to seeing what you all come up with on Tuesday.